Today we will take the first significant step in defining the Lebesgue measure on Rn. We will do this by defining what is known as the outer measure on all subsets of Rn. So, this would be a quantity defined on the power set of Rn. For each subset of Rn we define its outer measure to be a number using the cubes which cover this set. But this is not going to be a countably additive measure. We will have to restrict it to a subclass of the power set which would be actually a sigma algebra. This will be called the Lebesgue sigma algebra. On the Lebesgue sigma algebra, the restriction of the outer measure will be a countably additive measure. So, this would be a genuine example of a measure which is one of the most important measures you would come across. And the Lebesgue sigma algebra which I just mentioned will contain the Borel sigma algebra which we had already defined earlier. So, recall that Borel sigma algebra is the smallest sigma algebra containing all the open sets. So, we have lots of sets there. The Lebesgue sigma algebra will be slightly bigger than the Borel sigma algebra. In fact, it is going to be the completion of the Borel sigma algebra with respect to the Lebesgue measure which we would be defining using the outer measure. So, that is our goal in the next few lectures. We will take the first step by defining the outer measure today. So, let us start. So, let us start by recalling rectangles. So, we will be dealing with Rn. So, recall that closed rectangle was denoted by R. So, this is a product of intervals. So, A1 B1 cross A2 B2 cross etc. cross AN BN. So, product of intervals. So, in R2 it would be like A1 B1 here, let us say A2 B2 here, we have the box here. Okay. So, this is a rectangle in R2. Open rectangle would be a product of open intervals. Open rectangle, the product of open intervals. So, we have open interval A1 B1 dot 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 AN BN. So, that is an open set. Closed rectangle is a closed set, and you may have some of them to be closed and open and so on. So, you may have rectangles of various types where certain parts are not involved. For such a rectangle we define the volume. So, this is what we did in the last class. Volume of R is denoted by modulus of R. This is the product of the sides, length of the sides of the rectangle, j equal to 1 to n, right. So, in dimension 1, when n equal to 1, this is the length. When n equal to 2, this is the area, and when equal to 3, we have the usual volume. Okay. So, that is what we call volume of the rectangle, and we looked at some elementary properties. So, recall that recall if a rectangle R is the union of finitely many rectangles almost disjoint, then the volumes add up, right. Then modulus of R is summation j equal to 1 to n mod Rj. So, this was one of the things we proved. Second one is sort of easy. If R is contained in union Rj, j equal to 1 to n, then modulus of R is less than or equal to summation j equal to 1 to n modulus of Rj. So, the volumes, because some of the Rj's may overlap and you may get more area. So, that is very easy to see, and we also proved a topological result. A theorem we proved was every open set open set in Rn is a countable union of almost disjoint closed cubes. Okay, so what is a cube? So recall that a cube is a rectangle. A cube is a rectangle whose sides are equal. It means if Q is the product of A1, B1, etc., AN, BN, then B1 minus A1 equal to B2 minus A2 equal to Bn minus An. All the sides are equal. Then we say Q is a cube. So this is something which we proved. Every open set in Rn is a countable union of almost disjoint closed cube. So this is something which we will use at some point of time. Okay, so we will use it later. We will use this theorem later. As of now we do not need this, so we will just keep it as it is. So let us take the first significant step. As I was mentioning earlier, we define outer measure. Okay, so outer measure on Rn. Okay, this will be denoted by m star. So this is a standard notation we will use, m star. So how is it defined? So you take any set E of Rn, okay, define the outer measure of E by, well, it is going to be denoted by m star E. So it is m star of E equal to infimum of summation j equal to 1 to infinity mod qj, where qj are closed cubes. So recall that this is a closed cube is a closed rectangle whose sides are equal, and mod qj is the volume, it is the product of the length of the sides. Well, it is not just arbitrary cubes, it should cover E. So E will be contained in union qj, j equal to 1 to infinity. So let's read it again. It is the outer measure of the set E. So this is an arbitrary subset of Rn, right? E is a arbitrary subset of Rn. Okay. M star of E is first of all infimum of some quantities. So these are positive quantities, positive numbers, right? What are you doing? You are covering E. So this simply means that qj's cover E, and you take all such qj's, all such covers, construct this number summation j equal to 1 to infinity mod qj, then you take the infimum. So what are we doing? Let us look at some picture. Suppose I have R2 and I have some set E like this. So let us say this is my set E. What do? I am covering E with cubes. So it is like this. So you cover E with cubes. It need not be almost disjoint, or it could be any kind of cubes, closed cubes. Then you look at the union, look at the volume of these cubes, right. So it would be these things and then you add them. So, these are your QJs, right, and then you add them. So, you look at mod Qj. So, mod Qj is your volume of these cubes, and then you sum them up, j equal to 1 to infinity. So, you get a number for this. Now, if you take some other cube cover, so you may take some cube like this, some cube like this, some cube like this, and so on. You may cover E with some other cubes in some other form, and for those cubes you will get similar a quantity similar to this, right, and then you take the infimum of all such things, infimum of all such things. That will give you the outer measure of E. So, if you look at the picture, it will be clear to you that we are trying to approximate. So, we are trying to approximate the area of E by cubes, right, and we are hoping that this quantity which we have defined m star of E will give us the area or volume or length depending on which dimension you are, if the set E is nice enough. So, for example, if E is a cube to start with, then you will get its volume as m star of E. Okay. So, we will see some examples to understand this. But before we go further, there are things one should keep in mind. So, let us write down m star of E again. M star of E is simply infimum of summation mod Qj, j equal to 1 to infinity. The Qj's are closed cubes, and E is covered by the Qj's, j equal to 1 to infinity, right, and you take infimum over all such covers. So, there are things you should notice. One is, it is not enough to take finite unions. That will not give you a countably additive measure. One has to take finite and infinite covers like union Qj, and then you take infimum over such things. That is what will lead you to a countably additive measure. Then it is the infimum. So, infimum has certain property in the sense that if I add some epsilon to m star of E, so need to the definition implies this is something which we will use very often. Definition implies that for every epsilon positive there exists a cover Qj of E such that summation mod Qj, j equal to 1 to infinity, is less than or equal to m star of E plus epsilon, right, because m star of E plus epsilon is greater than the infimum, So, there is a number in the collection we are looking at, right. In this collection there is a number which would be less than or equal to m star of E plus epsilon, which gives us this cover Qj. This is simply the property of infimum, right. So, let us okay. So, this is the property of infimum. This is something which we will use all the time, infimum. Okay, keep that in mind. From the definition it immediately follows. So, from the definition it immediately follows that if A is contained in B, then m star of A is less than or equal to m star of B. Well, why is that? So, recall that m star of A, or okay, let us start with m star of B. So, m star of B is, you look at infimum of summation mod Qj, where Qj's are covers for B. So, Qj are closed cubes and B is contained in union Qj, j equal to 1 to infinity, right. But A is contained in B. So, if B is contained in the union of Qj, j equal to 1 to infinity, then A is also contained in the same Qj's, j equal to 1 to infinity, right. This would imply that m star of A is less than or equal to summation mod Qj, j equal to 1 to infinity. But this is true for any cover union Qj containing B, right. We started with cover containing B, cover of B, and we have proved that m star of A is less than or equal to this quantity. So, I can take infimum over all such covers on the right hand side, right. Take infimum over this collection, that will give me that m star of A is less than or equal to m star of B. Okay. So, as the set becomes bigger and bigger, the outer measure also becomes bigger. Okay. So, let us look at examples. So, we will keep the definition of m star here. So, if I take E is a subset of Rn, m star of E is infimum of certain quantities. So, infimum of summation mod Qj, j equal to 1 to infinity, Qj closed cubes and E is contained in union Qj, right. Okay. So, with this, let us look at examples, easy examples. One. So, take a point. So, take E to be a singleton, some point, x naught is a point in Rn. Okay. What is the outer measure of E? So, what is m star of E? Well, the point does not have any volume, so it should be 0. So, let us see why it is. This is because, so if I take any point x naught in Rn, I can cover it with a cube of volume less than epsilon, right. So, let us call this Q, where volume of Q is equal to epsilon or less than or equal to epsilon. This I can do for every, every epsilon, right, every epsilon positive. So, for example, on the real line we are looking at one point x naught and you can cover it with an interval. So, here the closed cube will be a closed interval. So, let us say x naught minus epsilon by 2 to x naught plus epsilon by 2. This is my Q. What is the volume of the Q? This is simply epsilon, and I can do this for every epsilon. So, m star of a singleton is less than or equal to epsilon for every epsilon positive. But I know that m star is also positive, right, because it is the infimum of positive quantities. So, it is greater than or equal to 0. So, this will tell me that m star of a singleton is 0. So, points have outer measure 0, which is what one should expect. Okay. Let us look at the next example. Example 2. Let Q be a closed cube. Q be a closed cube in Rn. Okay. So, recall that we defined the outer measure of any set using the volume of the Q's, right. So, mod Qj is simply the volume of Qj, right. So, one would want, or that should be the measure of Q, right. So, if Q is a closed cube, then well, then what is, we want to find out what is m star of Q, right. So, it is natural to expect, so natural to expect m star of Q to be equal to mod Q, right. This is what we want for the basic objects like closed cubes. It should be the volume of the Q, right, that should be the outer measure. So, let us prove this. Okay. So, proof. So, we will prove this one, that measure of outer measure of closed cube is actually the volume of the cube, volume of the cube Q. Well, so recall that m star is the infimum of certain things. So, we will prove that. So, we will show that m star of Q is less than or equal to mod Q and m star of Q is greater than or equal to mod Q. Okay. So, that will tell me that they are equal. Okay. So, one of them should be trivial, this should be trivial, this is trivial. Why? Because Q is a closed cube and is covered by Q itself, right. So, recall that m star of Q is the infimum of various things. So, this is infimum of summation mod Qj, where Q is contained in union Qj, right, closed cubes and so on. So, I can take just Q as the cover, right, just Q as a cover for Q. So, this would be simply mod Q in this case, and I am taking infimum of such things. So, I have mod Q as a number here and I am taking infimum of things. Since mod Q is here, m star of Q will be less than or equal to mod Q. Okay. So, this implies m star of Q is less than or equal to mod Q. We want to show the other way inequality so that they are equal. Okay. So, for that we use the definition. Okay. For the other way inequality, use the definition. Okay. Use the definition. How do we use the definition? So, let Q be contained in union Qj, j equal to 1 to infinity. So, we are taking one cover, right. So, take one cover for Q, okay, using closed cubes. Let me write this again. Q is contained in union Qj, j equal to 1 to infinity. For each, okay, so maybe fix epsilon first, fix epsilon positive for each Qj, choose an open cube Sj. So, it should be an open cube. Can write it again. Choose an open cube Sj such that Qj is contained in Sj, and so there are two things. So, one is this, and the volume of Sj, remember volume of Sj is simply the product of the length of the sides, is less than or equal to 1 plus epsilon 1 plus epsilon times mod qj. Well, this is possible, right. So, if I have this as qj closed, right. So, I have the boundary as well. So, this is my qj. I take a small open cube which is bigger than this, right. So, it is like this. So, that the product of the sides, that is the volume here. So, this would be my Sj. So, that the volume is less than or equal to 1 plus epsilon mod qj. Well, for on the real line what is happening? So, I have qj here. So, this is my qj. I take a slightly bigger open interval, right. So, that this inequality is true, that is trivial. So, that can be done. For each qj we get this. So, we get the closed cube q is contained in union j equal to 1 to infinity qj, that I know. Then I have chosen sj's. So, this would be contained in j equal to 1 to infinity sj. But remember, this is an open set, right. So, this is an open cover for closed cube q, right, because these are all open sets. Sj are open cubes. So, they are open sets. But q is compact. So, this is a closed cube. So, this is compact, it is a compact set, and I have an open cover. Okay. So, there exists a finite cover for q. Okay. Hence, there exists n such that, so this is maybe slightly bigger than the finite cover, does not really matter. Q is contained in union j equal to 1 to capital N Sj. Okay. So, I am still writing j equal to 1 to n. All of them may not be there, but some of them will form the finite cover, right. So, I had the closed cube q first, then I covered it with closed cubes qj's. I made them bigger, so that I have an open set and so on, and I chose finitely many from there, right. Because of compactness, I get a finite cover for q. Okay. So, this immediately implies, so remember this was one of the exercises, when you cover a rectangle with other rectangles, you have the volume inequality, which is summation j equal to 1 to n mod Sj. Okay. So, what did we prove? We proved that. So, let me keep that here. So, we have mod q less than or equal to summation j equal to 1 to capital N mod Sj, which is of course less than or equal to summation j equal to 1 to infinity mod Sj, because I am adding positive quantities. But recall that Sj's were open cubes chosen with some property. This is the property, right. So, I replace mod Sj with 1 plus epsilon. So, this I can bound by j equal to 1 to infinity 1 plus epsilon times mod qj. So, this is true for every epsilon, right. Now, there is no epsilon dependence. So, you look at this part and this part. For every, we started with an arbitrary cover, right. We started with an arbitrary cover of q, and for a fixed epsilon we have proved that we have this inequality, right. Q and qj's are fixed now, and this is true for every epsilon. Since it is true for every epsilon, I can let epsilon go to 0, right. So, this implies mod q will be less than or equal to summation j equal to 1 to infinity mod qj, because it is true for every epsilon. So, what did we prove? So, let's rewrite this. If q is contained in union qj, j equal to 1 to infinity, qj closed cubes, we have the volume of Q is less than or equal to summation j equal to 1 to infinity mod Qj. This is always true. Now, the left hand side is a fixed number mod Q. Right hand side I can vary the cover, right. I can vary the cover and take infimum. The left hand side does not change because it is a fixed number. So, I can do this for all the covers Qj's and take infimum. Okay. So, taking infimum on the right hand side gives mod Q is less than or equal to infimum of summation j equal to 1 to infinity mod Qj, right. Qj closed cubes and Q is contained in union Qj, right. That is how we started with. So, you are taking infimum over all such collection, which is this is the definition of m star of Q. So, let us recall the first inequality, which was easy to prove, showed us that m star Q is less than or equal to mod Q, and then we showed that mod Q is less than or equal to m star of Q. So, all this will imply that m star of Q is equal to mod Q. So, in this example we proved that if I have a closed cube, its volume is the outer measure. Okay. So, one more example 3. Okay. Suppose Q is an open cube. Q is open cube. Then also m star Q is mod Q. Well, that is easy because Q is contained in Q closure. So, open cube meaning without the boundary. If I take the closure, I will get the boundary, and that is a closed cube, and this would imply that m star of Q is less than or equal to mod Q bar, which is mod Q. And for any open cube I can approximate it by small closed cubes inside it, right. So, one more line, given epsilon positive, there exists a closed cube S contained in Q such that mod Q is less than or equal to mod S plus epsilon. Okay. Put together these two. So, I will let you complete. This will imply that m star of Q is equal to mod Q. Okay. So, we will stop for now. We have just seen what is the outer measure, which is defined for all subsets of Rn, and we have seen that it coincides with the notion of volume when the set is a closed cube or an open cube. Now, we will look at properties of the outer measure, and then we will see that it turns out to be a countably additive measure when we restrict it to a appropriate sigma algebra.